This silt has been mechanically pulverized and then passed through a number 40 sieve to remove all large particles. For the purpose of today's lab experiment, bentonite clay has been added to increase the plasticity of the soil. The liquid limit is defined by the moisture content in which a soil begins to act less as a viscous fluid and more as a plastic putty, like peanut butter. By convention, this is defined as the water content at which a groove cut into a soil pat in the Casa Grande apparatus requires 25 blows to close at a distance of 13 millimeters, 1/2 inch, the distance of this tool handle. We will need a few lab devices to help us with this. First, we will have the standard liquid limit device, also known as the Casa Grande apparatus. This will aid us in getting the blow counts. Next, we will need the grooving tool used to make a standardized groove in the soil pat. We will also need a couple moisture content cans for moisture content determination. We will need a water bottle so we can add moisture to our soil. We will need a mixing bowl to prepare our soil in, a spatula to mix our soil, a mortar and pestle to crush the soil if need be. We will also need a scale to record the weights of each test. The plastic limit is defined as the moisture content at which a material begins to act less like a plastic putty and more like a brittle solid. In order to conduct the plastic limit test, the following will be required. We will need a glass plate to roll out our 3 millimeter threads on. We will need a rod that is 3 millimeters in diameter to gauge when we get down to 3 millimeters. We will need 2 cans to get moisture content in, and we will also need a spatula to spread and dry out our soil. The documents pertaining to today's lab can be found on Blackboard in PDF format. The documents include the lab handout, the ASTM standards, and the data sheets. In order to produce the flow curve, 4 liquid limit tests must be conducted. 1 test between the blow counts of 15 and 20, another between the blow counts of 20 and 25, a third between the blow counts of 25 and 30, and finally 1 between 30 and 35. As the soil dries out, the moisture content is reduced. This results in stiffer soil. To perform the liquid limit tests, weigh out about 300 grams of the provided soil. If the soil is clumpy, you can break it up in the mortar and pestle. Add water from the water bottle and mix the soil until it appears uniform and the surface looks creamy. A proper blending could take up to 20 minutes. Determine and record the weights of the 4 tear cans, which will be used later in the test for moisture content determination. The Casa Grande apparatus is easily knocked out of calibration, so it is important to calibrate the device often. The grooving tool has a block on the back of it that is exactly 10 millimeters tall, the fall height of the Casa Grande cup. Calibrate the apparatus by placing the grooving tool underneath the cup. Rotate the handle so that the cam just contacts the cup. If the apparatus is calibrated, the cam will just barely touch the cup and it will not lift it off the grooving tool. Loosen the set screw on the top and adjust the thumb screw in the back to raise or lower the cup. Thoroughly clean and dry the cup. Evenly spread a moderate amount of soil into the cup to create a soil pat to be tested. Using the grooving tool, create a straight groove through the center of the soil pat. The shoulders of the grooving tool should just scrape the surface of the soil pat. If the shoulders do not contact the soil pat surface, too little soil has been placed in the cup and the test should be restarted. Once the groove has been made, rotate the handle at 120 revolutions per minute, 2 cycles per second, and count the number of blows it takes to close the groove in the soil pat 13 millimeters or 1/2 inch, which is the width of the grooving tool handle. If the number of blows falls between 15 and 20, scoop out some of the soil and place in one of the pre-weighed tear cans and record the new weight for moisture content determination. Place the can with the soil in the oven and reweigh it again in 24 hours. If the number of blows falls below 15, mix the soil to dry it out, clean, dry the cup, and repeat the test. If the number of blows falls above 20, add moisture to the soil, mix it, clean and dry the cup, and retest. Repeat the procedure to get tests between 20 and 25, 25 and 30, and 30 and 35 blows. Plot the moisture content versus blow counts and determine the liquid limit from the flowchart. With the moisture content plotted in the vertical axis and the blow counts plotted in the horizontal axes in log scale, a linear regression can be established through the data and the liquid limit can be interpolated. The plastic limit is the average of the moisture content when the soil starts to crumble when it is being rolled into a 3 millimeter thread. So you take a 25 to 30 gram sample, spread it on the plate to dry it out. When it gets to a workable state, you can pick it up and start working it in your hand. Start rolling the soil into a thread. Roll the soil until the diameter of the thread is reduced to 3 millimeters. The rod can be used as a gauge to determine when the soil has reached 3 millimeters in diameter. If the soil does not crumble when rolled down to 3 millimeters, further dry out the soil and try again. Once the soil crumbles at 3 millimeters, collect samples of the crumbling soil and place them in pre-weighed tear cans for moisture content determination. Repeat the test enough times so that enough soil has been obtained for 2 moisture content samples of approximately 6 grams each. Record the wet weights of the moisture content samples and place in the oven. Reweigh the samples again in 24 hours. The average of the 2 moisture contents is the plastic limit.
And I'm going to write down the mass, which is 241.32. Okay. So next sieve is 1.18 millimeters. It's 504.6.1. Next one is 2.36 millimeters. The mass of it is 540.51 grams. 475. 568.14. 9.5. 624. 115. Next one is 13.2. 592.93. And the final one, the top, the largest one, 19, will give us 715.33 grams. Okay, so we put them all together. Make sure that the largest sieve is on the top, the finest sieve is at the bottom. Now we will get some soil sample. We have lots of particles in it, so we need to randomly select soil for this test. And this is what we'll do next by using soil divider. This is a subsample that we will use for the test. We'll measure the mass of it. It should be about 250 grams. We'll make sure that all fines will go in the soil, back in the soil. It will make 234 grams of the sample. So next step is we pour the sample in the sieves. We'll do it nice and gently. Make sure all the fines will go back in the soil where they belong. We're going to cover it with the lid, and then we're going to put it in the shaker for 10 minutes. Well, the test finished. Now we can measure the mass of each sieve. We'll start with the top one. There is nothing in it. The second from the top, also empty. We have a little bit of rocks in the third sieve. We shouldn't shake it. We should be very careful so that fine particles will not fall through the sieve. Gently place it on the surface of the scale. We have a little bit more rocks in the next sieve. The next sieve will give us 593 grams. This is the pen, the final sieve. These are the final particles from the soil. That's it for the physical part of the test. Now we need to look at the data and do some simple analysis, calculations. We'll look at the amount of soil in each sieve, and then using this data, we can draw a grain size distribution. 0.6, 16.3. Okay. So this is a percentage. I rounded some of these numbers. And next step, we will draw a curve. So we draw it on this plot, where we have particle size in millimeters versus percentage passing. Particle size we'll get from the sieve openings in millimeters. And we will start with the lowest one, which is 1.18. What I will do is I will take this number, 1.18, as particle size in millimeters, and I will take this number from column 7 as percent passing, and I will plot it on the graph. So for 1.18, which is approximately here, we have number 16.3, which is about here. Next one is 2.36 millimeters. It's there. And then the number is 36.6. Somewhere around here. Next one, 4.75. It's around here, 4.75. And 4.75 correlates with 59.1%. The point is here. For next one, 9.5.
Start exactly where you are, sorry. I can see that piece of paper.
That's probably okay.
Oh, that's okay, is it?
That should be fine.
Okay. That's fine. Keep going.
For the size of 9.5, we have 96.1%. About here. Sorry, my mistake, 96.1, it's about here. And next SIEVE size is 13.2. We have hundreds. So these are the points, we can connect them so that we'll have grain size distribution curve. What you can do is you can draw it by hand manually, or you can use any software like Microsoft Excel. You can put all your data in the Microsoft Excel spreadsheets and then just draw a curve using one of their functions. That's it. Thank you.
Shear stress at any given time. In this lab-based device, the rotation is applied through a variable speed motor which can turn this horizontally geared wheel at different rates depending on what's desired. This rigid block is fixed to that surface, and so as the wheel turns, it moves around and eventually comes into contact with a blade on this horizontal bar. So that blade, or that point of action, is at a constant known distance from the center of rotation. That bar has 4 strain gauges, 2 on each side, which are connected in a Wheatstone bridge. And so a signal conditioner can monitor those 4 strain gauges as a load cell. And essentially what it's doing is measuring the bending moment as the rod in the center resists rotation and the block is pushing on this end. So those load cell readings can then be recorded to a computer at high frequency. And if we calibrate the system by applying known moments to look at the voltage output from the bending load cell, we can calibrate the system that way. That way we can look at the data file and interpret any voltage as a known moment acting on the vane rods. This is a 5-inch diameter tube sample that's relatively undisturbed, and we're going to use it for laboratory testing for multiple purposes. So we're going to want to compare the lab vane shear results with some UU triaxial results and a CU triaxial result that are all trimmed to this specimen geometry. So what we're going to do is essentially treat the specimen as quarters, and we'll run the lab vane in one quadrant of this undisturbed sample and save the rest of the material for extrusion later and using that for undrained UU testing and CU testing. So in order to insert the vane, we need to lift it up out of the way, slide the specimen underneath, and place it down. We don't want to be too close to the sampler edge, or we might be in material that's disturbed from the sampling process, but we also want to stay away from the middle of the specimen, or we'll disturb those other quadrants that we want to save for later. So we'll put it there, and we're going to insert it with some space between the block and the rod. I'm going to center it left and right a little better here. And then we want to just firmly and slowly insert the vane. We want to go well below the top surface of the soil because we want the soil to shear along that top surface of the vane itself. Now we're down to the level of the block. The vane is about 1.5 inches below the surface of the soil here. That's more than we need, but it's fine. And any torque that's registering here will be measured in the initial values in the data file, so we'll get that started. And now we're going to power the motor and turn this forward direction. And you can see the block is advancing here on the bar. I'm going to hold the sample so we don't get rotation, and we'll run the tests. Contact. So now we're rotating the vane within the soil, generating shear resistance. Reaches peak very quickly. We'll talk about why, and we'll let this go on well past the peak with the torque dropping with time. That's about 1/4 of a revolution. We're going to pause there for a second. And we've now already measured the peak shear strength of the soil when we saw the peak torque. The torque is directly related to the shear stress acting in the soil. One of the things that the vane shear test is very good though also is for soils that have some sensitivity, we can measure the peak strength and then we can measure the residual strength very easily using the same equipment. So what we're going to do is rotate the whole system several times to give us a remolded condition along the failure surface. I'm just making sure all the wires stay clear here. So that's 1.5 revolutions. We'll go out to 2 revolutions. We're going to stop. We're going to bring the rate back down to the initial slow rate and get readings at completely remolded conditions. So this is at the same strain rate now, but after very large shear strains have been developed along the failure plane. So this should be out in the residual case. And so we're getting essentially constant shear resistance now. It's no longer dropping, it's down at a residual value. And we can calculate the sensitivity immediately without even knowing the geometry of the vanes by knowing just the ratio of the torque. The peak torque divided by the residual torque is going to be the same as the peak shear stress divided by the residual shear stress. stop system there. If we were, we'll remove this.
Is a 4-inch mold having a volume of 1/30th of a cubic foot and a collar. A standard Proctor compaction hammer weighing 5.5 pounds and dropping 12 inches. 2 moisture content cans. A steel straight edge. A large mixing pan. A graduating cylinder capable of holding up to 250 milliliters. A spray bottle. A metal spoon, and a knife. We will also be needing a digital balance, an oven for moisture content determination, and a sample extractor. The soil that we will be performing the standard Proctor compaction test on is a loessile silt obtained from the Mississippi River Valley. The soil has been mechanically pulverized, then air dried. By conducting several standard Proctor tests at varying moisture contents, this curve can be established, and the maximum dry unit weight and corresponding moisture content can be determined. To perform the Proctor compaction test, start by weighing the empty Proctor mold without the collar. Record the empty weight on your data sheet. Also weigh the 2 moisture content cups and record their weights as well. With a caliper, record the dimensions of the mold so the volume can be calculated. Average 3 equally spaced diameter dimensions and 3 equally spaced height dimensions so that an accurate measurement of volume can be established. Weigh out approximately 2,000 grams of the provided air-dried soil. Now that we have our soil weighed out, the desired amount of water to add to the soil must be determined. The weight of the water that needs to be added to our soil can be determined from this equation. The weight of the water equals the weight of the soil, 2,000 grams in this case, times the final moisture content minus the initial moisture content. The final moisture content is the target moisture content, which I have selected to be 15%. The initial moisture content is all the water that is trapped inside the air-dried soil. This has been predetermined to be 2.5%. With 2,000 grams of soil, an initial moisture content of 2.5%, and a target moisture content of 15%, it can be determined that I need to add 250 grams of water to my soil, or 250 milliliters. Obtain the correct amount of water from the tap, and pour the water into the spray bottle. Using the spray bottle, add the water to the soil and start mixing it till it becomes a uniform color and consistency. When all the water is gone and the soil has been mixed to an even and uniform consistency, it is time to place the soil in the Proctor compaction mold. Start by placing the collar back on the Proctor mold. Spoon enough soil into the mold that when compacted, the soil mold will be filled approximately 1/3 of the height of the mold. Now you want to place the mold on a hard surface such as a concrete floor and compact with the Proctor hammer. Compact the soil using the standard Proctor hammer. Use 25 blows spaced evenly throughout the layer for proper compaction. After 25 blows, take the mold back to the table, scarify the surface, and add more soil for the next lift. Scarify the surface of the first compacted layer with a spoon. This will ensure that the second layer will bind to the first layer well. Spoon enough soil into the mold so that when compacted, approximately 2/3 of the height of the mold will be filled. Again, take the mold to the concrete floor and compact it with the standard Proctor hammer. The soil should fill the mold and extend past the top of the mold an 1/8 inch. Using the straight edge, trim smooth the top of the soil mold. Using the leftover material, fill any voids that might appear in the surface of the soil. Remove all the loose soil around the mold and weigh the mold without the collar. Loosen the soil mold from the base. With 2 hands, carry the soil in the mold into the extractor and extract the soil from the mold. Insert the soil and mold into the extruder. With 2 hands, carefully pick up the soil specimen and carry it into the other room. After the sample has been extruded, split the sample with your knife. Take samples from the top and the bottom and place them in the moisture cans for moisture content determination. Weigh the cans on the scale and record the weights. Place the cans in the oven. In 24 hours, remove the cans and record the dry weights. The dry unit weight of the compacted soil specimen and the moisture content can be calculated. From several iterations of this test, a plot of the dry unit weight versus moisture content can be determined. From this plot, the maximum dry unit weight and corresponding optimum moisture content can be determined.
Such as a caliper and or ruler, soil specimen, a bowl, as well as a tamper. Finally, a funnel will be necessary. Next, measure and record the inside depth of the cell without sand. Next, measure the thickness of the base plate. As well as measuring the thickness of each gripper plate. This will be used in further calculation for determining the height of the sample. Finally, located on the shear box is the diameter of the sample. Generally, one is to measure and record the mass of the shear box before and after filling it with sand, but for the purposes of this lab we will deviate from that and record the mass of the sand in the bowl before and the mass of the sand in the bowl after we fill the shear box. This will be discussed further in the lab video. Next, fill the shear box with sand using 3 separate lifts, tamping each lift, keeping the sand below the side screws. With this, record the remaining height from the gripper plate to the top of the shear box. Again, this will be used in a calculation that is discussed in a subsequent section of the video. After recording the final mass of the sample left over in the bowl, one may begin the actual shear test procedure. Insert the shear box specimen into the loading machine. Place the loading cap and frame without weights on the sample. Take the construction screws out, gap the sample, add weights to the loading frame, and then ungap the sample. Position and zero the dial gauges, horizontal deformation, vertical deformation, and shear force. Designate group members to track required data gauges. Tau equals F over A, where tau equals the nominal shear stress, F equals the shear force, and A equals the initial area of the specimen. Sigma equals the normal stress, N equals the normal vertical force on a specimen, and A equals the initial area of the specimen. The weight of the sand, as discussed previously, is calculated simply by taking the initial weight of the sand in the bowl and subtracting the final weight of the sand in the bowl. The height of the sample is going to be the height of the box minus 2 times the height of the gripper plate minus the height of the base plate, minus the height of the air gap. When all necessary calculations have been completed, one must plot the shear stress versus the horizontal displacement in Excel. Next, plot the horizontal displacement versus the vertical displacement. Include all specimen data on the same plot and label the normal stress for each curve. Finally, plot the Mohr-Coulomb failure envelope. This is the normal stress on the x-axis, shear stress on the y-axis. Both axes must be on the same scale. Determine the friction angle for the material and label it on the plot.
Weighted cylinder, some water, a veneer caliper, a mold, an empty bowl, a compaction device, an extraction device, a water content can, spatulas, a calculator, and an unconfined compression test load frame. The first step is to obtain the tare weight of your empty bowl. I have written down the empty tare weight, and I have obtained a sample filling up a good part of my bowl. I am now going to weigh the sample in the bowl. I will record this number. Now that this has been recorded, I can calculate I will then add the water to the soil, and I'm going to mix it thoroughly. Now that the sample has been completely melded and mixed, we're going to place it into the compaction mold and begin compaction. I can't talk. Place the soil into the mold as full as you can get it because it will compact. You see I have it full. Now I am going to use the compaction device to tamp the soil into the mold. Simply use the compaction device to push the soil until you do not notice that it is compressing any further into the mold. As you can see, the soil has compressed very much into the bottom of the mold. We're going to repeat this until the mold is fully compressed. The soil is now compacted to a level into the collar of the mold. It is now complete. I will now remove the mold from the holder. And lift it out. I'm going to take the ring apart from the mold. And as you can see, I have my soil. The next step is to ensure that the top surfaces and the bottom surface of the soil in the mold is smooth. Since I have some indentations, I'm going to patch with the soil from the ring.
Keep doing that.
Okay, now that my indentations are filled, I'm going to use a spatula to smooth the surface. The surfaces are now smooth and we are ready to extract from the mold. The extruder will have the handle in the upright position and the mold will slide into the extruder and set in the indentation. The handle is now in the upright position. I'm going to use one swift downward stroke to extrude the soil sample. We are now going to measure the diameter of the specimen at the top and record, the center of the specimen and record, and the bottom of the specimen and record. We are now going to measure the height of the specimen as well, 3 times 120 degrees apart. Write this down. Rotate 120 degrees. Record that. And the final 120 degrees. And record. The next step is to weigh your extruded specimen. Be sure to record that weight. The specimen is now ready to be placed into the load frame. We are now going to place the specimen in the center of the load frame. The next thing that we're going to do is turn the crank in a clockwise direction until the top plate is just touching the top of the specimen. You now must ensure that this pin is touching this pin so that you may get your measurements correct, and we're going to zero this dial. What we are going to be doing is observing these two dials as we turn the crank. The first dial is the amount of load that is being applied to the specimen. It is measured in divisions. Divisions are simply the measurements on this dial. Using the calibration connected to your device, you should have a ring constant in the corner of this paper. This ring constant will simply convert these divisions into pounds to indicate how much weight was used to induce failure in your specimen. The second dial is a displacement dial, and it will measure in portions of an inch how much your specimen is displaced as it is being failed. We are going to turn the crank very slowly in a clockwise direction. Every time this needle passes 1, 2, 3, 4, any of the major points, a reading will be taken of this dial. Please note that every time the needle of this dial passes 0, that is 1. So if it passed 0 and is at this point, that will be 1.10. We're now turning the crank very slowly at a rate of 0.25 inches per minute. You must not turn the crank too quickly or you will induce failure before you have had a chance to take your measurements. Once your sample failure has been sketched, you may unload the specimen, remove it from the load frame, and take a water content of your entire failed sample.
With GeoProbe systems, and today we're going to show you pushing CPT with our 3126 GT. Some unique features of this machine are the CPT functionality that's built into the machine right from the factory. You can turn on the CPT functions and it controls your head rate at 2 centimeters per second, and you can also limit the hydraulic downforce of the machine at 40%, 60%, 80%, or 100% of total hydraulic downforce. Some of the components we'll be using today are our new 10-12 anchor system. So you can see you've got a 10-inch flight at the leading edge with a 12-inch flight halfway up the extension. This gives you almost double the reaction force. We also have a rod guide, that provides lateral support for the rod string as you get into some tougher pushing conditions. We have a bridge that slides onto the toes of the machine, and that's what the anchor pulls against. and then a pinning bracket, and then when we go to pull, we'll use a rod grip pull handle, just like many of you are used to on any traditional geoprobe machine.
Setup begins with the drill mast already extended out from the rig. A dual flight anchor is advanced using the standard auger drive on the 3126 GT. The first flight is 10 inches followed by the second 12-inch flight. The anchor bridge is then slid onto the foot and the drill mast is retracted back towards the rig. A pinning bracket is then connected to the anchor to hold the foot to the ground for pushing. Next, a rod guide is attached between the toes to keep the tooling centered as it is advanced. Once anchoring is complete, the CPT logging equipment is set up. A string pot tracks vertical movement of the head to record logging depth. The end of the string is secured to the drill head. The CPT microphone also attaches to the drill head. This is used for pushing the cordless CPT system. A corded CPT system can also be run with the 3126 GT by using a seismic CPT push-pull cap. CPT data is recorded into the field laptop. The rig is now set up to begin pushing the CPT cone. Automatic head feed rate control advances the cone at the steady 2 cm per second specified by ASTM standard D5778. This provides hands-free operation during advancement of each rod. Rods are added until the desired logging depth is reached. A rod bushing is placed onto the rod guide to keep the rod centered while pushing. The 3126 GT has 15 tons of push and 24 tons of pull. Once logging is complete, the CPT system is ready to be retrieved from the subsurface. The string pot and microphone attached to the drill head can be removed at this point as well as the rod guide. Next, the pinning bracket is removed from the anchor. The head is side shifted over and a rod grip pull handle is used to pull each rod. Using the rotary drive, the anchor is removed. This completes CPT logging with the 3126 GT.
So there you saw just how quickly and easily you can set up the 3126 to push CPT. Some of the other unique features of this machine, you saw us using the side shift head of the machine to go from rotary to pushing cone underneath the microphone. When you're doing your traditional geotechnical borings, you're not moving your foot of this machine. You're using the side shift of the head to transition from your auto drop hammer to your rotary head or the direct push head if you're using our traditional geoprobe tooling. Also, unique features to this machine for geoprobe is the hands-free controls on this machine. You saw I was using this for when I was running the cone system. That controls your head feed. And then you've also got hands-free controls for the rotation of this machine. So if you're doing rock coring or mud rotary, you can use the hands-free controls. Very nice when you're doing those long runs there. Another feature of this machine is a 7-inch breakout that you saw us using during this video. We swung that in and we clamped the rod to keep the rod from sliding back down the hole. So very important when you're running CPT. You always want to bring your tools back out of the hole. Another option available for the 3126 is the CPT package. With that, you get the computer tray up here at your control panel for easy mounting of your laptop that you're running your acquisition software on. And then you also get this third toolbox, which holds the interface, microphone, cones, things like that for when you're in the field. If you have any additional questions or would like to see a demonstration of this machine, please don't hesitate to get
Could you make us move to your right. Right 500 millimeters. Right 500 millimeters. 500 millimeters. Half a meter. Half a meter. When he doesn't listen, I gotta next time I'll put him on trolley. Yeah, just